We are Vitric Engineering. I'd like to thank all of you for staying till the bitter end here. I'll introduce the team first. I'm Nate, the project manager and geotechnical engineer for the project. We have Bella, our environmental engineer, Jay and Jared, our structural engineers, Ben, our transportation and auxiliary structures engineer, and Peter, our water resources engineer. So for today's goal, first we'll talk about the project itself. Then we'll get into the key design elements that all of our engineers worked on this semester. Then we'll touch on the construction costs at the end and show you some 3D renderings also. So for the project background, we are doing the City of Valparaiso Public Works and Utilities Department project. Their current location, we are here at the university. Their current location is here to the southwest, right by the law school. And then the new facility will be here to the west of downtown Valparaiso, off of Joliet Road. So their current location is outdated. They have limited space, and they generally cannot fulfill the needs of the Valparaiso community. So the city already owns the new site. They've been using it for years. They've been dumping their street sweepings there for about 30 years, so there's some problems there. And is uphill from a protected wetland, so whatever goes on needs to be done carefully to protect the wetlands. Here's the current facility to the south of campus, Valparaiso University's campus. You can tell there's a lot of different buildings. They were all built at a different time, and there's a lot of their vehicles are outside, so they're racking up maintenance costs because they can't store their vehicles inside anywhere. At one point, they're actually storing some vehicles in their salt barn, which is an issue. So they wanted a new place that they can better serve the community here. So what they need in their new department, or their new campus, is office space for both utilities and public works employees, shop space for equipment maintenance of utilities and public works department equipment. They also want indoor vehicle storage to save money for vehicle maintenance. They need a salt barn for storing the road salt that they use in the winter. They also need a refueling station to refuel their vehicles on site. And then the site also needs some environmental remediation, as it has been used for 30 years as a dump site. So here's the plot of land that the city owns. Here's Joliet Road up here and the access road that they've created over years of dumping various things at the site. Down here is the wooded and wet area that is the wetlands that we need to protect while we build this site. So our project purpose is to generally build a facility that can allow the public works and utilities departments to address the needs of the Valparaiso community now and in the future. And we also need to remediate the impacts that they have impacted the site with. So here's a general overview of what our design is. You can tell we have our road coming in from the already paved road up here. We have two main buildings. This is the vehicle storage facility, and here is our office with our mechanic shops. Down here is our salt barn and refueling station, along with some other water resources components, such as a bioswale and a detention basin that you'll hear about a little later on. So for the geotechnical portion of this project, there were several things that were involved. First was a soil investigation. Next were mechanic pits to be inside the building. Then the foundation for the main buildings, which will be a deep foundation of driven piles. Then the connection of the piles to the building columns. And then finally, a grading plan for the site. So the soil investigation, we start with soil borings that were given to us by the client. Those say what type of soils we have underneath the site and where they're located. Using those, we develop soil profiles. Here you can see there's several different types of soils, and it changes as you move throughout the site. So we made a couple of those to use to govern our design later on. The next step was the mechanic pits. So these are going to be concrete pits in the ground of the building. You might have seen these like at Jiffy Lube last time you were there. The dimensions of those will be 6 feet deep, 5 feet wide, and 15 feet long. The 5 foot width allows you to put both these regular sized pickup trucks that the city owns, as well as like the larger dump trucks and vacuum trucks that they have. So this is a picture about what you can expect with a mechanic pit. It is a pit that is in the ground for people to work on vehicles. So then next was the main building foundation. That's a system of driven piles. There's 92 piles in total. They're all 1 foot diameter steel pipe piles that are closed-ended. Here's a picture you can see. The pile starts off above ground. Use a hammer to push it down into the ground. And we'll utilize a sand layer that's underneath our site. That's 15 feet deep for the office and shop building and 25 feet deep for the vehicle storage facility. The top layers of soil are clays, so we're going to use the sands underneath to support our building. Here's a basic diagram of the pile locations. Every dot is where a column is for the building, and that's where all of our piles will be. And that's what a steel pipe pile would look like. It's a steel pipe, and it'll be in the ground. So the next step is to connect our building to our foundation. That'll be done with a concrete pile cap. The dimensions of that is 4 foot by 4 foot square and then 2.5 feet thick. And that's just essentially a piece of concrete that sits on top of the pile. On top of the concrete cap will be a steel plate that is connected to our column, and that's how all the loads will be transferred down to the piles. Here's a diagram of that. You got the column on the top, concrete here, and the steel pipe at the bottom. The next step was a site grading plan. So we want to move water away from our buildings. We don't want water running into our buildings. And the site grading plan will help us treat our stormwater effectively. Peter's going to talk about that a little bit more. But here's what a site grading plan looks like. Each line represents 1 foot of elevation change. So here you can see our building, it's flat. The way this works is if you drop water here, it'll move perpendicular to these lines. So if we drop water here, it'll go down here into our bioswales and eventually into our detention basin. So with that, I can hand it off to Bella, our environmental engineer, to tell you what she did.
For the environmental component of this project, there are a few key design elements. These include the street sweepings and road spill on site that Nate has mentioned, contaminated soils due to the street sweepings and road spill that have accumulated, vapor intrusion, and protection of the surrounding wetlands. So it has been used for 30 years, so it has a lot of accumulation of contaminants. These are VOCs, hydrocarbons, and arsenic. They have migrated into the ground and caused contamination. The selected alternatives for all of the components of the project include thermal remediation of the contaminated soils, encapsulating the street sweepings and road spill within a clay liner, subslab depressurization underneath the office building and paint and sign shop, along with a few erosion control measures. For the contaminated soil, all excavated soil on site does have to be remediated, and it will be reused on site after remediation. The proposed alternative for this is thermal treatment with the use of a thermal desorber. The way the thermal desorber works, it treats the soil to a very high temperature to remove all contaminants. And the contaminants do have to screen below item screening levels. This is Indiana Department of Environmental Management. There is a large amount of soil on site, so we had to use a pretty large thermal desorber, and it has a pretty high removal efficiency. The way this works, the contaminated soil will go into the thermal desorber. It'll be treated and then tested to be under the screening levels for the contaminants. And if it's clean, it'll be ready to be reused on site. And all the vapors, there's a bag house that will remove particulate matter and the vapors, as long as the thermal oxidizer, which will further treat the vapors before going into the environment. For the road spill and sweepings on site, this is a little schematic of how the system will work. It's not to scale or anything, but it'll be within compacted bentonite clay. This will make sure that no leachate migrates into the soil and causes more contamination. And it'll be located up at the top corner of the project site, and there will be the entrance road across a portion of that as well. For vapor intrusion, this is a design that was designed to ensure that city employees are not harmed by the vapors that are due to the contaminated soils that were not remediated or excavated. The design was a subslab depressurization system. It's consisted of crushed stone, perforated pipe, and a vapor intrusion barrier. These are just a few pictures of them. The fan will be outside. There will be a fan as well that's outside the building that pulls the vapors from underneath. This is a little schematic. You can see the crushed stone is a permeable material that allows the vapors to travel through it and will be pulled through the pipe into a fan outside of the building. And then there's a fabric barrier right underneath the concrete slab to ensure no vapors get through. This is a practical vapor intrusion mitigation strategy, especially for new buildings due to having to be constructed underneath this slab. And for erosion control, These measures were taken to ensure that no pollutants are gone into the surrounding wetlands. There will be contouring 10%. These are a few pictures. It'll be a 10% slope going into the wetlands with vegetative barriers. Pictures right here. They'll catch any of the pollutants going traveling toward the wetlands, and then a flat terrace at the bottom. And I'll pass on to Jay.
Alrighty, thank you, Bella. So I'll walk you guys through a couple key components here of the structural portion. So we started off the year, we were looking for a couple of things. We knew that they had some space issues at the old campus. We needed to design a layout and figure out the square footage of some new buildings for them. And also we had to determine some building loading requirements and evaluate a few different alternatives for how we were going to deal with those. And so the end product we were looking for here was a detailed list of member specifications, as well as some detailed drawings for the office, paint and sign shop, and mechanic spaces. So I'll walk you through the building I was primarily responsible here on site. It's one building comprised of a few different areas here. We have the office, the paint and sign shop, and a mechanic space for the public works and for the utilities people. So you can see on the site map here, we're taking a look at this building right here. And it's comprised of the 4 areas there. We have the office space up front, the paint and sign, and the mechanic spaces. Our building will have a width of 70 feet and a length of 375 feet long. Here's kind of a 3D rendering here to give you a little vision of what we're looking at here. So our building will be a steel braced frame building. And you can see lots of garage doors there. We have the mechanic space for the public works and the utilities there. Lots of bays and access for them to work on vehicles. Here you can take a look at this picture here. Give you a good idea of what kind of materials we're using for the building here. So you look at the top there, we have some steel I-beams that will take the loading from the roof. It will carry those over to the columns there, also steel I-beams. Those will carry those down into our foundation that Nate talked to you a little bit about. And we will have a 6-inch reinforced slab that our building will sit on. That will carry all the loadings from the vehicles over the mechanics bays, also down onto the foundation there. Now I'll pass it along to Jared here. He's going to talk to you about another building on campus.
Thank you, Jay. So I am also a structural engineer, so I have much of the same design criteria as Jay did. So I also had to develop a layout and square footage for the garage to start, and then I had to figure out what the loading requirements were going to be that was going to be put onto the garage. And then once I have those design loadings, I can design the members, and then ultimately I'll end up with drawings to be built. So I'm going to be talking about this structure here, which is going to be the vehicle storage unit, or just simply the garage. So this is some drawings that I came up with. So it is 130 feet wide by 325 feet long, with columns being spaced every 25 feet. You can't see it very well in this picture, but it's going to be braced along this row, and then these 2 center rows there, which will look something like this up top. And this drawing also illustrates some of my choices for the members that I picked. And here is an aerial view of the garage here. As Jay stated, it will be a steel braced frame as well. And with that, I will pass it off to Ben.
Thank you, Jared. All right, so I had the auxiliary structures on the site, which are basically the other ones. Those included the salt barn and the refueling station. The salt barn is what it sounds like. It's a big building that holds salt. They needed enough capacity that they could store all of their salt that they need to clear roads in the winter. And then the refueling station is there so that they can refuel their vehicles that they have on site, as well as any other vehicles that the city owns in addition to that. And then both of these structures are going to be steel moment frames. The salt barn will have a fabric canopy similar to like a giant picnic tent. And then the refueling station, if you need an example, just walk to Speedway. The transportation portion had 3 key design elements. The first was the auxiliary lane, which is a flyby lane in more colloquial terms. Then the driveway onto the campus, and then the parking facilities. For the auxiliary lane, it was a bit of a challenge. On the far left down there, you can see that there's a 25-foot measurement, and that is the right-of-way to the railroad tracks just to the left, or what would be just off the left edge of the screen. Normally, we'd like the 180-foot run out on both sides, but it's a little squished down. That being said, having the auxiliary lane will still improve traffic flow for the neighbors in the residential area just down to the west edge of the project site. For the driveway onto the campus, I designed it. It's pretty simple. It followed much of the existing roadway that they had on the campus site that they'd been using for their trucks and everything that they'd use for dumping their road spoil. I did slow down the design speed and sharpen the curves a little bit so that the larger vehicles had to be a little bit more cautious entering the site if there were visitors or commuters or anyone else. That would be an additional safety feature for them. And then finally, one of the things that we really want to emphasize about this is that we found a way to use permeable pavers on our project site. This helps with infiltration, makes the campus a little bit prettier, and we also, well, in order to do that, we had to route all of our industrial traffic away from that parking area. And this also means that when visitors come onto the site, there won't be large vehicles attempting to turn them into pancakes. Yeah, and that's it. And with that, I will hand it off to Peter for the water resources design.
Ben? All right. So for the water resources design, there are 6 components. There are bioswales, detention basin, filter strips, rain gardens, permeable pavers, and stormwater sewers. Here you can see the general layout. Filter strips run the entire length of the road through the whole campus from east to west. You can see that there are 2 bioswales that lead to a detention basin, permeable parking spots that Ben just talked about in the commuter parking lot, and rain gardens to the north of the buildings. Bioswales are essentially large trenches that are densely vegetated that will take out pollutants and slow down water rates. This is good for our site because we'll have contaminants coming off of the heavy-duty vehicle trucks and coming off of the roads. This will treat those and allow the water to be a better quality. A detention basin is used to store water volume that is displaced by creating land that won't, land that won't let water enter the soil. Detention basin will take up that volume area and allow all that water to be stored until it can either infiltrate through the bioswale or exit the site through a pipe. Filter strips are used, they're essentially dense vegetation. They're used in Bella's design for erosion control, but they also create treatment for pollutants coming off of the roadway. To the west side of campus, that is our primary treatment. It's graded at 10% so that the water is slow enough that it gets treated by the grass and then enters our protected wetlands, keeping it wet and allowing water to exist there. This is a general overview of the design of a rain garden. Soil and gravel will be imported to allow more volume for water storage. And there is also a perforated pipe designed here, as the soils in the area can't allow very much water to go in them. If there's a large rainstorm, water is allowed to exit out that pipe and into the stormwater sewers. These rain gardens will be planted and look very nice, will be aesthetically pleasing to everybody, and they will also provide the drainage for the buildings. The stormwater sewer layout, it can be seen here. There's entrances at each of the 3 rain gardens and one from the main detention basin. They all connect together and run to the entrance of the campus where it will connect with the assumed city stormwater pipe. Next, I'd like to hand it off to Nate. He'll talk about our final cost.
Okay, so after all of the components that we just walked you through, the total cost for both construction and design comes out to $6.1 million. So next we have just a few 3D renderings. Some of them you've already seen, but we'll just go through them one more time. So here's looking south on our campus. This is the office space with the shops, and then here's the vehicle storage facility. Down here is the view looking north. You can see the refueling station with the salt barn, and another shot of the vehicle storage building. Here's a close-up of our fueling station and our salt barn. And then with that, I'd like to bring the group back up and we can see about any questions. Thanks.